In doing stoichiometry calculations, we assume that reactions proceed to completion, that is, until one of the reactants runs out. So, if we write in a reaction that is H2O, which in gaseous state, then carbon monoxide CO gas, that gives me H2 gas plus CO2 carbon dioxide gas. Okay, so this is my reaction. This water and gaseous state and carbon monoxide is reacting with each other. They're reacting with each other to give me H2 and CO2. So over the time they are making one mole of this, and 1 mole of this is making 1 mole of this and 1 mole of this, right? So since they are produced, so they will react with themselves, right? So they will react with themselves to come to this, to give me this back, right? Yes. So in this case, we can see that my reactants are reacting to give me products, and again my products are reacting to give me my reactants back. In this case, we express our chemical equation in this form, and this is called chemical equilibria. So what is chemical equilibria? When the concentration of my reactants and concentration of my products are constant over the time. They're constant over the time, and the rate of the forward direction, that means the rate of this water and carbon monoxide, the rate, how much they're making the products. So this rate will be equal to the reverse reaction, these two equations. So in order to study chemistry, in chemistry, each and every word means a lot. So since I said the rate, we have to study rate. In order, I said stoichiometry, you have to study stoichiometry. You have to have very good knowledge about stoichiometry, rates, and every word that comes in your study when you study chemistry. Okay, so I think we will make more videos on chemistry, so don't worry about that. If you know it, then you're fine to study chemical equilibria, and if you're not, then search in Google, watch some other videos, just make sure that you know that information. If not, I will make more videos on that. Okay, let's come back to here. If I make a graph, okay, so and the x-axis, this is my time, and y-axis, this is my concentration. This is my concentration. So as I have at the beginning of the reaction, I have a lot of H2O, 1 mole. I have 1 mole of carbon monoxide, right? So this is a lot. Let's say my reactants are here. So what happens to my products before the reaction starts? I have no products. I have only my reactants. So my products are at 0. 0. Here, my products. So if I graph it, my reactants, let's say they're coming down, right? And so this is my H2O. So this is my carbon monoxide, CO, right? And so since they're coming down, my reactants are decreasing. The concentration of my reactants are decreasing. So the concentration of my products should increase. They're increasing. They're increasing. Let's say H2 increasing, and this is my carbon dioxide. They're increasing. So in this graph, since I have very large amount of my reactants, they're coming down in the middle, and since I have very small amount of my products, they're coming up, they're going up, they're increasing. So at this stage, you can see the concentration of all my reactants and products are constant, they're not changing. This is called chemical equilibrium. It's in order to study chemical equilibrium, it's very important to find out and to know what chemical equilibrium constant is. I talked a lot about chemical um, equilibrium constant in the previous video. So let's say I have a reaction. It's J moles of A plus K moles of B. That that is in equilibrium. So getting I mole of C and mole of C. Okay. So how can I write chemical equilibrium constant? We define it as K. So K is equal to chemical equilibrium constant, right? It is always reactant over product. Reaction C raised to the power I, C raised to the power M. This square bracket mean that this is my concentration and this is A, B, K. Okay. So I set it as my chemical equilibrium constant equation. Let's solve a problem based on this chemical equilibrium. So based on this chemical equilibrium, I can say this is Kc in terms of concentration. That's why I'm writing C. I can find out the same equilibrium constant in terms of pressure. P, Kp. Kp would be the same actually. So this is based on concentration, this is based on pressure, and that's all. So the pressure of C raised to the power I, pressure of B raised to the power M, pressure of A raised to the power J, pressure of B raised to the power K. This is same. One is based on pressure, one is based on concentration. So we have a relation between Kc and Kp. and I took it in the last video. Okay, so let's say I have um, this reaction N2O4 gas that's in an equilibrium giving me 2NO2 gas. Okay, how do I find Kc? Guess the amount I need all concentration at equilibrium. And the temperature, let's say my temperature is given 298 K, 298 Kelvin. I have N2O for my concentration is 4.50 times 10 to the power negative 2, times 10 to the power negative 2, M molarity, that means mole per liter, and I have NO2 as 1.61 times 10 inverse 2. That's also my concentration. So these numbers are given. I'm just solving example. These are given. I'm just showing how to plug this number. Just remember how do we write Kc and Kp as always reactants over products. So what is my product here? What is my product? NO2. This is my product. Raised to the power the coefficient, that's a square. This is 2, I have 2. Okay. So the concentration of N2O4. Okay. So let's calculate, let's just plug in the number, the temperature, this is constant. Okay, that doesn't change anything in my Kc value, the equilibrium constant. NO2, I have 1.61 times 10 inverse 2, then to the square, and this one I have 4.50 times 10 inverse 2. So just calculate using the calculator. Okay, using nines, 1.61 times 10 to the power negative 2. Okay, negative 2. Okay, that's square. Okay, and divided by 4.50 times 10 power negative 2. Okay, so I find out it's 5.76 times 10 to the power negative 2. And for K, no units. Don't have to be worried about a unit. I will explain it on another video why K does not have unit. That's all. Thank you very much.